What's up? Spencer here. Just going over video presentation number 1 for fluid dynamics, fluid engineering, I guess you'd call it. All right, so this problem, gauge extends 1.2 meters into the page for mass, blah, 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 blah. I'm sure you've already gone over tons of these. So to start off, we're going to need a couple things that we can just look up. Those are going to be the specific weights of our two fluids in the problem. So if you go ahead and look those up on the charts provided, we get that the specific weight of glycine, I'm just going to go with that. We're going to call that specific weight G is equal to 12,400 Newton per meter squared, and our specific weight for water is going to give us 9,800 Newton per meter cubed, my bad. All right, now that we have those out of the way, we're also going to need the area of this gate right here. And so we're told that it extends 1.2 meters into the page. So the area for that is just going to be 1.2 meters times the 1 meter. That's going to give us 1.2 meters squared. Alrighty, now that we have that squared away, we can get into the free body diagram of the problem. Alright, so we're just going to do the free body diagram of this gate right here. Draw it out like that. This is going to be point A, this is going to be point B. So point A, we have A sub Y and A sub X, like so. Here we have force B sub X acting. Gate, we're going to do this as 60 degrees. Alright, so we have two forces, or three, I guess. Main forces acting on this. It's going to be the weight downwards at the center of gravity right there in the middle, and then we're going to have the force from the water acting on the gate and the force from the glycine acting on the gate. Glycerin, I think it's glycerin. Anyway, disregard my pronunciation. So we're going to go ahead and throw those in there. Oh, a little crowded right here, but we're going to call this one force water. Actually, we're going to call that force from the right side, which is going to equal our force from the water. And then we're going to throw the other one up here. This is going to be the force from the left side, or the force of the glycerine. Wow, I keep just butchering that. That's incredible. All right, anyway, we're going to draw this. So this distance right here is going to be our y sub r term. And that's just the moment from distance from point A to where the force is acting on the gate. And then this term is going to be our YL. It's the same, just on the other side. All right, so now that we got our free body diagram down, we know that the gate is 1 meter long. So we're going to go ahead and say that this distance is 0.5 meters. And from there, I think we can start the setup of our problem. Something to just go over as well. So this gate is obviously a right triangle, angle of 60 degrees right here. So this being 1 meter, this component right here is going to be 1 meter sine 60. That's going to be our y component for the gate, this right there. And then this is going to be 1 cosine 60, just for future reference. Alrighty, with all that said and out of the way, I think we can start our problem. So we're going to go through this just like the quiz. On the left side here, we have we're going to need force L is equal to the specific weight times the height, HG, which we're going to solve for real quick, times the area. And so the height, the HG term, is going to be this 2 meters right here minus, so this looks like this is where it's acting. Sorry about that. I got a phone call from my doctor right in the middle of that. So we're just gonna resume. All right. Where were we? All right. We were going over, yeah, right. So left side, calculate the force L, force of the left side. So in order to find this distance, we're gonna call this distance h sub g. This is gonna be our 2 meters. Actually, this is the distance to the center of gravity. I guess you could call it hcg. Just to the center right here is gonna be our 2 meters minus our 0.5 sine 60 we got from above. And we used 0.5 here instead of the 1 because we were taking it at the center, which we can assume is 0.5. So we do the 0.5 sine 60 meters, and that's going to give us 1.57 meters for our hg term for this formula. So when we plug all these numbers in, which we have down here and right there, it's gonna give us, this is our 12,400 Newton per meter cubed times our 1.57 meters times our area, which is gonna be 1.2 meters squared. Units cancel, and that leaves us with our force on the left side equaling whopping 23,361 newtons. All right, now that we have the force, we need to go ahead and find the y sub L term right there. And so that's the distance acting on the force, not this hg term. This is the distance from the A to the force vector acting on that. So in order to find that, this is the equation we use. It's going to be I sub c, just the moment of inertia, over I sub L A times A plus our y sub c term. And our y sub c term is here. We should probably write that down too. Y sub c in our case is just going to be 0.5 meters. And this is because this is just the 0.5, it's just this 1 meter cut in half. That is our term. It's going to make more sense once we get this y sub L term. All right, anyways, when we plug our numbers in here, actually simplifying this down, it's going to be the moment over y sub c, or y sub L term goes to hg over sine theta times the area plus y sub c. When we plug our numbers into this, it's going to give us 1/12 base times height cubed over hg sine theta plus y sub c. Alright. That leads us to 1/12. Base of this thing is just going to be 1.2 times our 1 meter, that distance cubed, and times our 1.57 over sine 60 times our area, which is going to be 1.2 meters. Meters. All right. Can't forget the plus. Plus our 0.5 meters, which is our y sub c term. All right. From there, that gives us an answer of 0.546 meters. It's a little bit sloppy there, sorry. All right. Going back to this I sub t term, we can just clarify this up real quick. This is just the moment of the gate, which is a rectangle in our case. So this base times height cubed, base is just going to be our 1 meter, of the rectangle, and then basically going to be the 1.2, which is the depth into the page, which you can't see in the picture, and then the height is just going to be our 1 meter. And then this y sub c term that we got as 0.5 is just trying to clarify that up real quick. If we take this out, it's going to give us 0.046, and that is 0.046 from the center point. So 0.046 down this way would be the term we get if we take away that 0.5. But once we add it, since it is from the center of gravity right there, it's going to give us this distance all the way down to this point. If that hopefully that makes a little bit more sense. All right. So now that we have everything done for the left side, we can move on to the right side. Oh. And from there, we can do the same process. We're going to do our F. So the right side is going to equal the specific weight of water times the H of water height times the area. And in this case, our height water is what we're actually trying to find. So it's going to be our height term, which is what we're looking for in the problem, minus our 0.5 sine 60, like so in the above example. And so when we get that, we get our height with the water term is h minus 0.433 meters. All right, plugging these things in, it's going to give us the force of R is going to equal 9,800 Newton per meter cubed times R. We're just going to leave this as our H2O for now. Times our area, which is again 1.2 meters squared. And that gives us 11,760 H sub water. That's going to be in newtons. All right. Now that we found the force of the resultant vector, we're going to move on to the move on to the position. So that's going to be our y term. And just like above, we're going to use the formula of the moment over our y sub r distance times a plus our y sub c term, which is then going to lead us, of course, into, we're going to sub this out for the h height, this time for water though, over sine 60 times the area plus our y sub c term. Plugging our numbers in, we're going to get the same on the top, 1/12 times 1.2 meters times 1 meter cubed over, and so this fraction right here, we're actually going to move the sine 60 up to the top since we are dividing by a fraction here. We can add the sine 60 to the top here, and that leaves us with height in regards to the water over here times the 1.2 meters squared for the area. And that is going to, oh, we can't forget our y sub c term, plus our 0.5 meters. Alrighty. All said, that comes out when you type it in the calculator to become 0.072 meters over our H of H2O. This is supposed to be an H2O up here, my bad. H2O plus 0.5 meters. All right, so now that we have these four things, oh, not that one. Cool. These are the four things that we need in order to solve for this height in the equation. So to do so, we are going to take the moment about point A here. So we know that the sum of all moments about A are equal to 0. From there, we can determine that the moment is going to be equal to force on the left times distance, y sub L, minus force on the right times the distance for the right, plus our weight here. In this example, it's going to be 180 kilograms times 9.8, mass times the weight, or mass times the gravity, to give us a weight times our 1/2 or 0.5 cosine 60, which is going to be the distance here that the weight is acting down from the center of gravity, and so the distance to that is just going to be our 0.5. Sorry, not that. Actually, down here. It's going to be this distance right here is going to be our 0.5 sine 60. All right. From there, we can just plug and chug our terms in. So we're going to get 23. So 0 is equals to 23,361 newtons times our distance of 0.546 meters minus our force from the right side, 11,760 times our H2O newtons times our distance, which is going to be 0.072 over H2O. This is nice because these two H2Os are going to cancel, plus our 0.5 meters, plus our weight, which is going to be our 180 kilograms as given in the problem, times the acceleration due to gravity. It's going to give us our weight times our, pencil keeps breaking, 0.5 cosine 60, not sine 60, meep, my bad, cosine 60 degrees. Probably said sine 60, meant cosine 60. It's going to be this distance right there, 60, this whoop, whoop. Distance acting from the center, point A to the center of gravity right there. That is going to be our 0.5 cosine 60 as we see right there. All right, so doing that, that's going to give us, plugging in, 12,750 Newton meters minus these two H2O terms are going to cancel, but you're going to be left with one remainder, given this 0.5. So we're going to get minus 847 Newton meters. And then we're going to get minus 5,874 times our H2O value meters. And these two terms are here as just given by distributing that to the given. There. All right, and then our last term is going to be 441.45 Newton meter. Cool. From there, we can just bring the H over to one side. 5,874 H2O. It's going to equal, plug this into the calculator real quick. 45 minus 847. Probably should have done this earlier to save time, but it's okay. 12,344.45 And this gives us our height term as 2.1 meters. Sorry, so we're almost done. That is not our final height that we are looking for. Our final height that we are looking for is just going to be our h. Sorry about that again. My doctor called me again to go in there today because I got stitches in my head, unfortunately. But anyway, sorry about that. Where were we? We were at, we just calculated the height to the, what's it called? This is not our total, this is not our final height here. Our height total that we're looking for in the problem is going to equal our 2.1 plus 0.5 sine 60, which is our y term here. And that's because they are asking for the entire height in which the normal force will be 0, not just to the resultant vector, which is, we found the height to the resultant vector right there, the force. So in order to get the height total that they're asking for, we need to add that y term from the triangle we drew earlier up here, but cut in half. So we're using the 0.5 as we've described earlier. And so that's going to give us a height total of 2.53 meters. And that is our final answer. Go ahead and look sign it here. It's an awful signature. My signature is very inconsistent. Anyway, that is going to do it for our problem.